Okay, so what's the problem with the computers these days? They're made out of tiny parts that everyone calls transistors. But how do they make those transistors like do all those stuff and stuff? This is a transistor. It is a square. Okay, fine. It might be a little more complicated than that. It has those stuff sticking out of everything. A transistor can behave in exactly two ways. One, on. Two, off. Oh, fine. It can do a little more things. 3, be destroyed. 4, be created. But the problem is that when you have all these fancy transistors, then how do you use them to make a computer? You'll just get a bunch of binary storage instead of a computer, right? And that brings us to our first question. Like my animation. Anyways, why do computers exist? To solve the questions, we need a fact. Transistors are small. Oh, and another fact. Transistors consist of electricity flowing through them. That's also why if you make stuff too powerful, then it'll have to get bigger at a point. Because once the transistors reach a size of 1/5 of the size they are right now, then the electricity might just quantumly teleport to the other side. Which is still pretty confusing, but back to our topic about the old computer that works even though it's just made out of a jumbled part. Okay, let's go back. Say there's a group of ants. Each ant releases chemicals when it touches another ant. An ant is a pretty dumb thing itself, but if you put a bunch of ants together, then somehow it makes a smart ant. Yes, and that's exactly why people are talking about this theorem. 1 plus 1 equals 3. Well, it actually means that the power of 2 people added together can be more than just adding them up if they work together. That's also what the transistors in the computer I'm showing you right now do. Oh, well, you can't see it? Oh, I was using it for recording. Anyway, the transistors work together, and you're like, how do you do that? Yes, transistors are not people. But they can still work together, can they? Here's a bunch of plain old transistors. Now let's draw some connections. Aha, connections. But anyways, how do people get that idea? It's not like ideas pop out of nowhere. Oh, I'm going to change this a little bit. Yeah, right, just giving them different shapes. Just tell me if my drawing skills are getting clunky. Yes, it's getting clunky. Anyway, that's what's supposed to be going on inside your brain unless you're not a person. I guess if you're watching this video, then I can assume that you're a person, right? So that's what's going on inside your brain. But how do they connect? And what do the transistors actually do? Aha! You're probably pretty confused when you first saw this. I didn't mention the term neural network anywhere in the video before. I mean, I didn't actually say it, but this is supposed to be part of the title of the video you're watching right now, assuming that you didn't hit pause right now, like just a few seconds ago. A neural network is like a bunch of neurons. Neurons do not look like this. I'm bad at drawing. Connected. Yes, they are working together. Okay, we're just exaggerating the connections to make them a little easier to see. The connections do not look like this in real life, just a note. And neurons also don't look like that in real computers. But anyway, let's still assume that that is a neuron. Wait, it just disappeared? Oh yeah, stuff was supposed to disappear. Anyway, still like that. Neurons are just stuff like that. But still, a neural network is a bunch of neurons working together. We're going to have a bit clearer of that. If you want to do that, then just skip ahead to chapter 5 where we'll give you some examples. No, you might miss chapter 3 and 4. Why they put it in Roman numerals for it to look cooler. Okay, binary neuron. Behold, the binary neuron, the simplest neuron of all. Okay, fine. A binary neuron has two states, on and off. Unlike the other neurons, identity neurons and sigmoid neurons, the binary neuron is much more simple. It can only output at two states, which I showed you. If you want it to be a little more clear, then I'll text 1 and 0. That's what they're supposed to represent. Yeah, you can use them to make a neural network. Seriously. Go to the next videos and you'll see how these simple neurons can make the addition function in your computer. Also the subtraction function and the multiplication function and the division function. But for the handwriting programs, you might need some help from the identity and sigmoid neurons. Anyways, we call this binary neurons. But what are the neurons anyways? Well, neurons are not square stuff. In a typical neural network, you have a few stuff called the input and a few stuff called the output. I guess I don't have to explain to you what those are. The inputs are the stuff you get to change, and the outputs are the things that the two examples we'll make only have one input and one output, and they're only one layer. Yes, you can stack them up in layers. In fact, if you couldn't do that, then your computer wouldn't be able to do addition. But I guess you get my point now, and you know what a neuron is. Okay. A logic gate. Say you have a bunch of transistors. You smush them together. Like your cells. You have to give them names for a group of them, not just one of them, or else building computers would get a lot more complicated because you would have to go with more names and you might have to give names to groups of transistors and they would be silly. Yes. So, anyway, this is what a logic gate looks like. No, this is not this is actually a logic gate. It looks like this. Oh, fine, that's the symbol. Should I draw another one for you? There's 8 logic gates. There's supposed to be 8. They have these symbols. And maybe I should write the text later. Okay, this one is actually the one that most people forget. And this one, which is the only one of this one, which is one of the only 2 logic gates that need a hidden layer to operate. More about that later. And they're opposites. The most common logic gate that pretty much everything forgets about. Okay, the arrow everyone forgets about. Even in those books where you have those logic gates, they still forget about it. Maybe I made them up. This is and. No, wait. That isn't and. Nope, I need this to be a little. Hey. This is or and doesn't have a name. Though sometimes they like to call it ought to follow the pattern. Or I mean not the most famous and no, which most people pronounce and spell incorrectly. Most people think it's Nexor. Next or. That doesn't sound really nice, so I guess they decided to change it to XNOR. Oh, well. Fine, maybe my drawings weren't so good. So, let's go find some better logic gates. The better logic gates are at the computers because they are good at generating images. And by the way, every time I say computer, it reminds me to might take some time. Let's see. This is where we can find nice logic and or XOR. I figured out they call it buffer and nor XNOR and not. I figured out they only included the buffer thing because they because if because neurons are sort of annoying and they can only connect with a neuron on the next layer, so they used it to space stuff out. I figured it out. And you need both of them to light up. For the OR gate, you only need one of them. But if you put both of them in, then it's still fine. But for XOR stuff are different. If you put both on, it doesn't. It only lights up if one of them is on. No. I mean buffer. It basically does nothing, okay? It was only created by crazy people who thought it was useful. Just kidding. You actually need it in the circuit. You actually need it in the network in which you do addition on. NAND. It lights unless both of them are on. Which is sort of weird. But we must move on. NOR. If just one of them is on, then the thing turns off, which is even weirder. XNOR. If both of them have the same, if both inputs are either both on or both off, then makes it light up. Okay, last one, not. Reverse this. Anyway, those are the logic gates, which I took sort of long to explain, and they didn't really explain how you're supposed to connect them, but that will be soon. We needed to finish the rest of the half of the progression. And there. We don't need our annotate tool for now. Here we have this simple gate. It's pretty simple. Click, click, click. It's a logic gate. Oh, fine, I'll draw it. It's a game of can you recognize the symbol? Cool. It is that sort of triangle thing, right? The one on the top is the same as the one on the bottom, but let's see how this works. This is a connection. Okay, there are 5 colors of connections. Dark green means that it has a weight of 2. Light green means it has a weight of 1. Gray means that it totally has no effect, aka it has a weight of 0. Light pink means it has a weight of -1. And dark pink means that it has a weight of -2. First, it seems pretty absurd to use negative numbers as weight, but before that, you'll be wondering what a weight is. Okay, seems like I didn't fully explain how to connect stuff to a neuron. Every neuron has a bias, in which I clearly showed by putting B equals 1. Yes, most people use B for the bias because B is the first letter of bias. This every connection also has a weight. Every not connection that still involves layers that involve neurons with layers that are exactly one apart, you still call it a connection. It just has weight 0. Weight can actually be any number, but let's call this I1 for input 1. Oh yeah, I should use text. I1. We call this W1. Call this B. So then this output is if I1 times W1 minus B is less than 0, then the value is 0. But if I1 times W1 minus B is not less than 0, value 1. Those are the rules. Okay, but don't go looking for a neural network right away. Why? Because this is a really simple one. It only has one input. Later you'll find them stacked in multiple layers and with multiple inputs. But the rule is still the same. You add all of the inputs, multiply by their corresponding weight, and then subtract the bias. If it's less than 0, the value is 0. If it's not less than 0, then the value is 1. And hidden layers, well, you just treat that as 2 networks. And you feed the output of one into the input of the other. Make sure to do it in order, but you don't have to. Anyways, if you said, what's the use of having a negative weight? Here it is. You need it to make the not happen. Because this is always less than, and this is always greater than or equal to. You can't flip it or else you'll violate the binary neuron. You have to make this a negative weight, but then it can't get over 0 to 1, so I had to change this bias to 0. This is also a logic bit. It is called not. Clearly. This time the weight is light pink, which means that the weight is -1. For this gate, we could we can simplify it as if I1 is at least 1, then value equals 1. If I1 is less than 1, which means that it has to be 0, value equals 0. And that's exactly what this thing runs on. Now what if we simplify? Now we'll simplify it for the NOT gate. Now there's different rules for NOT. If I1 less than or equal to 0, value equals 1. And this can only be possible when the input is 0, because remember, 2 possible inputs for these type of simple networks. 1, 0, 2, 1. Or 1 on, 2 off, or 1. Well, I can't think of anything else. Still fun to play with it. Let's go through the cases. In this case, it is 0 in the NOT gate. 0 is at most 0, so the value is 1. Right, I made another mistake. But this, I1, the input 1 is greater than 0, so the value is 0. The switch gate. In this one, I1 is less than 1, which means that its value is 0, but now I1 is at least 1, it is 1, so then the value is 1, which is basically how my 2 really simple networks work. Which is also how this video is supposed to end. No, wait, we need a summary. Just write it on text. Hope you can read it fast enough. No, actually, I'm going to wait. Okay. That is my summary. I'm just going to wait until you're done reading. Wait. You can always pause a video, can't you?